Sections 4.2 Mean Value Theorem. In this section, there are two important theorems we're going to cover. Two important theorems. One is called Rolle's theorem. And the other one is the mean value theorem. That's the big theorem here. What are we going to do with Rolle's theorem? What is Rolle's theorem? We're going to look at the conditions. Each theorem has its own conditions. If the conditions are met, then each theorem said we can have this thing, which we can use in calculus, basically. So what is Rolle's theorem? Let's say let f be a function that satisfies the following hypotheses. First one, f is continuous on the closed interval AB. It's very important to see these conditions. It must be continuous on the closed interval AB. So that means including the endpoints A and B. F is differentiable on the open interval AB. So we don't care if it's differentiable at the endpoints or not. And the last one, f of A equals f of B. These are the three conditions. If these three conditions are met, then Rolle's theorem said, then there is at least one number, let's call it C, in the interval AB, in the open interval, so it can be at the endpoints, for which the derivative of that function at C means the slope of the tangent line at that C is 0. The slope of the tangent line at that point is 0. So how does that work? Let's look at it graphically, see what happens. Say this is the function, xy plane, and so that's the function f. Let's say A is here and B is here, so that's f of A equals f of B, as you can see. So one of the conditions, f of A equals f of B. As you can see, the function is continuous, f is continuous over the closed interval AB. F is differentiable over the open interval AB. So continuous, no jumps, no holes, nothing. Differentiable, there's no like cusps, there's no like vertical tangents. Then this is saying there is a point somewhere in between A and B, so that at that point there's a horizontal tangent. So at least one point, so that's a C. So there exists a C in between A and B, so that f prime at C is 0. So this means at that point there's a horizontal tangent. Can it be, you said there is at least one C. Let's look at it. How can that happen to have more than one C? Let's say we have a function like this. This is the function f, and say I'm gonna pick the interval from here to here. So A, this is f of A, this is f of A, and well, let's move it to the left a little bit. F of B, f of A and f of B are the same. Over that interval from A to B, notice the function is continuous and differentiable. So there are 2 points here. I'm gonna call it C1. That's where we have a tangent line that is horizontal, and there's another tangent line here that is also horizontal line. So this is telling us that f prime at C1 is 0 and f prime at C2 is 0. So let's look at other examples. Let's look at a different kind of examples. Let's say we have a dot here as part of the graph and the function goes this way. So let's say A is here and B is here. So notice f of A and f of B are the same. So f of A is okay equals f of B. The function f is differentiable. I'm going to write diff means differentiable over the open interval AB. But there's a problem here. The problem is that f is not continuous at x equals A. So that fails one of the conditions of Rolle's theorem. So this means we can conclude there must be a C somewhere between A and B so that there's a horizontal tangent at that point. So the continuity condition fails. Remember, it must be continuous from exactly A to exactly B. It's continuous everywhere between A and B, but it's not continuous at A. Now, I don't care if it's differentiable at A, because the condition said f must be differentiable over the open interval AB. It doesn't say exactly from A to exactly B. That's one kind of like special example that fails the Rolle's theorem. Let's look at another one. So say A is here, B is there. Do you see f of A equals f of B? Okay. So that condition is okay. F of A equals f of B, it's met. Is it continuous? So this is the graph of the function f. F is continuous, it's fine, continuous over the closed interval AB, that's fine. Wait, it's not differentiable somewhere between A and B. So let's call this point here T or something. Note f is not differentiable at x equals T. So this means one of the conditions is failed, and hence Rolle's theorem cannot be applied. Let's look at another example. Say this is A and this is B. And this is the graph of f. So notice f of A equals f of B. So it's okay. F is continuous over the closed interval AB. That's fine. Oh, wait. F of A does not equal f of B. So it's continuous and differentiable. F is differentiable over the open interval AB. But it's not. F of A does not equal f of B. Watch why. F of A is here. I didn't see it right away. And f of B is there. They're not the same. So this condition failed to work, and hence the whole theorem failed to work. But continuity and differentiability, both conditions are met. So that's okay. Now we're going to look at not graphical examples, but an actual given function. So let's say they ask us to verify that each function, given function below, satisfies the three conditions of Rolle's theorem. On the given interval. So then we're gonna find the values of C between the interval, let's say AB, that guaranteed by the Rolle's theorem. So let's look at the first example. Y equals f of x equals x squared minus 3x on that closed interval 0, 3. First thing, we say f of x is a polynomial function and hence continuous. All polynomial functions are continuous. Hence continuous on the closed interval AB, which is 0, 3 in this case. And also f of x is differentiable, or you can just say f on the open interval 0, 3. What about f of 0 and f of 3? Are they the same? Well, let's see. That's a 0 squared minus 3 times 0. That's 0. And f of 3 is 3 squared minus 3 times 3. 9 minus 3 is 0. So they are the same. So the three conditions of Rolle's theorem are met. This means now we can say now by Rolle's theorem, there exists a number C in the open interval 0, 3 so that f prime of C is 0. This statement here will help us to find out the values of C. So let's write the function again, the given function x squared minus 3x, and find the derivative for that, which is 2x minus 3. If we find the derivative of C, at C, that's 2c minus 3. This must equal 0. And then that will enable us to solve for C, which is 3 over 2, or 1 and 1/2. Make sure that value C, the value C we obtain, really falls inside that interval 0 to 3. Does it? 1.5? Yes, it does. So that's what we need. This is the value C we're looking for. Let's look at another example. Y equals f of x equals x to the 4th minus 2x squared plus 1 on the interval -2 to 2. Let's see what happens. Same thing here. We see that the function, this function f, is a polynomial function. And hence continuous on the closed interval -2 to 2 and differentiable on the open interval -2 to 2. So these two conditions, you must state them. Do not just say continuous differentiable. Say it's a polynomial function. State why you think it's continuous and differentiable. So this is important to say it's a polynomial function. And then you need to see if the third condition is met, f of -2. If we substitute -2 to the 4th minus 2 times -2 squared plus 1 and calculate all of this, 16 minus 8 is 8 plus 1, 9. F of 2 is the same thing. 2 squared plus 1, that will give us 9. So that proves that f of -2 equals f of 2. So the three conditions of Rolle's theorems are met. Then by Rolle's theorem, we say that the derivative, which is 4x cubed minus 4x, there is a number C, 4c cubed minus 4c equals to 0. Now, how do we solve this? How do we solve this out? Is we can divide first by 4 and then factor a c out. So c squared minus 1 equals to 0. Then c times c minus 1, c plus 1. So c here is going to be either 0, c equals 1, or c equals -1. We have three values. Remember, the values that we pick, they have to fall in that interval they give us. Are they between -2 and 2? Yes. So these three values are all fine. That's why in the statement of the problem of the theorem, I said there's at least one number C. So this means you can have more than one value for C. Let's look at another example. Y equals f of x sine 2x on the interval 0 to pi. Well, we all know that this function, this trig function sine from over 0 to pi, f is continuous on the closed interval 0 pi. F is differentiable on the open interval 0 to pi. And if I find f of 0, that's sine 2 times 0, 0. Sine 0, 0. And f of pi, sine 2 pi, which goes back to 0, so it's 0. So these are the same. F of 0 equals f of pi. So what we have here, the three conditions are met, 1, 2, and 3. Then by the rules theorem, it says that the derivative, which is, what's the derivative of sine 2x? By the chain rule, is 2 cosine 2x. There's a number c somewhere between 0 and pi, so that f prime at c, cosine 2c, is 0. We need to solve this equation now. Cosine 2c is 0. What's the smallest, or what are the values of c that would make cosine 0 or 2c? Well, 2c can be pi over 2. That's the first one I come across on the unit circle. Cosine pi over 2 is 0. The next one is 3 pi over 2. The next one, 5 pi over 2. And this list can go on and on. Odd multiple of pi over 2. If you divide by 2, each one of them, you get pi over 4. 3 pi over 4. Next one, 5 pi over 4. And this list can go on and on. Now, how many of them are between 0 and pi? The first one I know is between 0 and pi. This one's still less than 1, like the 3 over 4. But 5 over 4 is 1 point something, so it's more than 1 pi. So the only values of c that work here, there are two of them, pi over 4 and 3 pi over 4. So that gives us, variety of examples how we work with rules theorem, how rules theorem help us to find or guarantees that you can find at least one c between a and b, so that the tangent line at that point or points is going to be horizontal tangent line. So now let's look at a slightly different kind of example. Let's say state y rules theorem cannot be applied to the function f. Let's look at the first one. X squared minus 2x plus 1. And the interval from -2 to 1. Well, we know this is a polynomial function, hence continuous and differentiable. So let's focus on the third condition, f of -2. That would be a -2 squared minus 2 times -2 plus 1. 4 plus 4 plus 1. That's 9. What about f of 1? It's 1 squared minus 2 times 1 plus 1. 1 minus 2, -1, plus 1, that's 0. Notice f of -2 does not equal f of 1. So this is the condition that fails the rules theorem. Let's look at another one. F of x equals x to the 1/3 minus x on the interval -1 to 1. On the interval -1 to 1. So the first thing I'm gonna do is, I don't know how this function looks like, but usually if you have exponents, like rational exponents like this, rational exponents, that reminds me of differentiability. So if I happen to find f of 1, I get 0, and f of -1, maybe that might give us 0. We don't know. We can test it later on. But for the meantime, I'm gonna check how to fail or pass differentiability here. Let's check that out. We find the derivative of this by bringing the 1/3 down, subtract 1, minus 1. Then we don't like to see negative exponents, so we bring that down to make it positive. So what does that mean? This tells us that f is differentiable except at x equals 0. What makes the denominator here, what makes this denominator 0 is x equals 0. And notice 0 is in that interval, -1 to 1. So if when we say a function is differentiable from -1 to 1, means it's differentiable over the entire interval from -1 to 1. Means it's differentiable at every single point in that interval. But 0 is within that interval and it's not differentiable at 0. So the function fails the differentiability condition. That's why Rolle's theorem cannot be applied. Let's look at another one. F of x equals 1 minus x over x plus 2 on the interval -3 to 0. Well, let's check out differentiability. Yes, I can find the derivative. What about continuity here? Well, the domain here, everything except -2, so x cannot be -2. So at -2, there's a vertical asymptote. So this tells me f is not continuous at x equals -2, which is in the domain -3 to 0. So the continuity condition fails to work, and that's why the Rolle's theorem cannot be applied to this function. Now we do we go over the main theorem, which is the mean value theorem. Mean value theorem. We might abbreviate with MVT, mean value theorem. So again, if a function f satisfies the hypothesis that f is continuous on the closed interval AB, f is differentiable on the open interval AB. Notice so far they match the conditions of Rolle's theorem. And guess what? There's only two conditions need to be met. We don't need f of A and f of B. If these two conditions are met, then there is at least one number C in the interval AB so that f prime at C, like the slope of the tangent line at C, equals f of B minus f of A over B minus A. That's what the theorem says. So what is this? The left hand side is the slope of the tangent line. This is the slope of the tangent line to f at C, at x equals C. That's what this is. Well, what is this f of B minus f of A over B minus A? What does that remind us about? This is the slope of the line, which we call it secant line, connecting the 2 points. So what they are saying, the slope of the tangent line at C equals the slope of the secant line that connects points A and B. So what does that mean? They have the same slope. Same slope means they are parallel. So if I want to show you graphically how that works, so let's say that's the function f. And then I'm going to pick the interval from A to B. Well, if I project this up, this is f of A. If I project this up, Let me move this up a little bit. This is f of b. If I connect A to B, like these 2 points, that's the secant line. This is the secant line, connecting the 2 points. So what the theorem said? The theorem said somewhere between A and B. So there is at least one number C between A and B somewhere, so that you can draw a line, a tangent line to F that is parallel to the green line, parallel to the secant line. I see one of them is here. I can draw a tangent line here, which is parallel to this one. So this point here is C. But wait, I can draw another tangent line there. See? So that's, I'm gonna call it C1. This is C2. So that's what the theorem said. The theorem said if it's continuous on the closed interval AB and differentiable on the open interval AB, then we can find at least one number C between the two numbers A and B, so that the tangent line at that C is parallel to the secant line connecting A and B, connecting these 2 points. That's what the mean value theorem says. How can we do it or apply it here? Verify that the function f of x equals x cubed minus 3x plus 5, let's say over negative 1 to 1, satisfies the condition of the mean value theorem, then find the value or values of C. So C is the constant. Well, again, as we did in Rolle's theorem, so we say f is a polynomial function and hence two things: continuous, so it's continuous over on the closed interval negative 1 to 1. So it's continuous on negative 1, 1, differentiable on the open interval. So it's continuous on the closed interval AB, differentiable on the open interval AB. Those are very important to state within the solutions. So since the two conditions are met, then the mean value theorem guarantees then by the mean value theorem, there is at least one number C in the closed open interval negative 1 to 1, so that, notice in the problem we will talk about A and B in the theorem. So this is our A, this is our B, so that the derivative of the function f prime at C is f of B, which is 1, minus f of negative 1 divided by B minus A, 1 minus negative 1. So here on the side, I'm going to write the function again. It was x cubed minus 3x plus 5. The derivative of that function is 3x squared minus 3. We're going to substitute C in here. So 3c squared minus 3. F of 1, if we try to plug in 1 in for x, you get 1 minus 3, negative 2, plus 5 is 3. Minus f of negative 1 is negative 1 plus 3, that's a 2 plus 5, 7, over 2. So then you get 3c squared minus 3 equals negative 4 divided by 2 is negative 2. So 3c squared is 1 if we add 3 to both sides. Then c squared is 1/3. And c is not just one square root of this. A lot of people think like, okay, that's the square root of 1/3. It's not. It's a plus or minus, which we call the square root property. Very important. So you can rewrite this as 1 over square root of 3 and you can rationalize. Make sure the value of c we get, or the values, they really fall between -1 and 1, which they do here. So these are the c values we were looking for. Let's look at another example. F of x equals natural log of the square root of x on the interval 1 to e the 2.7. This function, if you like to rewrite it, you can rewrite the square root as 1/2 and bring it down. We know how the graph looks like, right? The graph of ln of x like this. This function is continuous, so f is continuous on the closed interval 1e, and then f is differentiable on the open interval 1e. So what we have here, I found that it's continuous differentiable. Then by the mean value theorem, there is a number c in the open interval 1e, so that the derivative at c is f of e minus f of 1 over e minus 1. Always on the right side, I come on the right side, I have 1/2 ln of x. We find the derivative for this, which is 1/2 times 1 over x. So if I want to substitute the c in, I get 1 over 2c equals f of e. What's ln of e? Ln of e is 1 times 1/2, 1/2. Ln of 1 is 0 over e minus 1. Remember, we need to solve for c. Cross multiply. What do we get? 2c times 1/2 minus 0, 1 times e minus 1. So c equals e minus 1. Remember, e is about 2.7 minus 1, so that's 1.7. Does that fall between 1 and e? Yes, it does. So there's only one value of c that satisfies the condition. Now, what about if they give us slightly different kind of example? Let's say, suppose that f of 0 is -3 and the derivative of x less than equal to 5 for all x. How large can f of 2 possibly be? So we're going to look at this question. There's no mention of Rolle's theorem. There's no place where they mention mean value theorem. There's no place where they're asking us use the mean value theorem or use Rolle's theorem or use anything, you know. So there's no mention of any of the theorems. So if you see a question like this on the test, you're gonna go like, wait, what is this? How am I gonna find f of 2? The first thing I think about, they are doing f of 2 here, so f of 0, and then they're asking about f of 2. So basically, maybe we are gonna work on the interval 0, 2. So I came up with an interval 0, 2. Now they told us that the derivative of x is less than or equal to 5. So how do we start with this one? There's no mention about the function is continuous or differentiable, but they said that the derivative exists, it's less than or equal to 5 for all x. So this means it's differentiable there. over 0 and 2. Since it's differentiable, so f is differentiable over the interval 0 to 2, then we have a theorem that says if a function is differentiable, then it is continuous. Sorry, we have to make it open. So if function is differentiable means continuous, then f is continuous over this interval that we chose. So they meet the mean value theorem conditions. We know f of 0, but we don't know f of 2. We're trying to see how large f of 2 can be. So I don't think Rolle's theorem can be applied here. So we're gonna try to see if we can use the mean value theorem. The mean value theorem said since the two conditions are met, there is a C between A and B so that this condition is met. F of B minus f of A over B minus A. Like that. So what is C? C can be any number between 0 and 2. So I'm gonna call it f prime of x. X is any number between 0 and 2. And remember I chose the interval 0 to 2, so that's A and B. So that's like f of 2 minus f of 0 over 2 minus 0. So let's see. This is given to us as it's less than or equal to 5. So we can write this equation as inequality like so. And did they give us more information? Oh, they give me f of 0 negative 3. So let me substitute that in. F of 0 is negative 3. 2 minus 0 is 2, less than or equal to 5. Then on the top we get f of 2 plus 3, cross multiply or multiply both sides by 2 is 10. Then subtracting 3 on both sides, that gives me 7. So this is saying the value of the function at 2 at most can be 7. So we can say that f of 2, the maximum value of f2 is possibly 7, or it can be 7. So that's like an indirect way of using the mean value theorem. That's what this section is about. It's like, what is Rolle's theorem, what is mean value theorem, and how can we use it in indirect way, as you see in this example. So the Rolle's theorem has more conditions, like one extra condition to use, but the mean value theorem has only 2 conditions need to be satisfied. One common mistake students do over the exams is they do not list the conditions in the proper way, like the way it's supposed to be listed. So you must say it's continuous on the closed interval and it's differentiable on the open interval. Those 2 conditions, most students, they just ignore them when it comes to writing down solutions when applying either one of the theorems. So that's what this section is about.